So, welcome everybody. My name is Jeremy Gibbons from the University of Oxford. I'm going to be talking about composable references, and this is joint work with my student Guillaume Boisseau, also at Oxford. So this is it's a talk I've given in various places in various styles, and so it's a different talk here because it's a different audience. I'm going to try and give you a flavour of this thing called the Yoneda lemma. That's the other half of the title. And the Yoneda lemma is, has been called the most important result in category theory by a well-known category theorist, Emily Real. And here's a bunch of maths that says what the Yoneda lemma is. And if you can read the category theory, that'll be all very familiar because it's a central result. And if you haven't seen this before, then it'll be completely opaque, I expect. I'm not expecting that to be particularly readable. What I want you to get out of that is it's a very short, sweet statement of something. And I'm going to explain what something is. And then I'm going to tell you what it has to do with these things called composable references. So composable references are accessors into data structures. So accessors, things like the getter and setter for a field in a record. That's a reference to the field in the record. So let's start with the Yoneda lemma. Roughly speaking, what the Yoneda lemma says is that you can understand a thing by understanding its relationships to other things. The thing is determined by its relationships to other things. And in a suitably abstract setting like category theory, that is a definition of what the thing is. It is nothing more than its relationship to other things. Category theory is the study of things and their relationships. So you've abstracted everything away, and the relationships tell you all you need to know. And this is an idea that actually comes up in lots of places. There's a saying in English that you can tell a lot about a person by the company they keep. And the Yoneda reading of that is, you can tell everything about a person by the company they keep. There is nothing more to them than the company they keep. And that completely determines them. So it's kind of a life lesson almost. And you see this coming up in other languages as well. I know this saying has equivalents in languages like Dutch and German, and maybe many other languages too. In Japanese, I'm no expert in Japanese, but I'm told that the Japanese word for human being is made out of two kanji. The first one means person, and the second one means between. So in Japanese, human being is what it is to be related to other people. It's the correspondence between, it's the relationship between you and other people. In Euclidean geometry, so this axiomatic geometry that used to be taught to all school kids, there are these things called points, there are these things called lines. Any 2 points determine a line. Any 2 lines that are parallel cross at a point. And you don't need to know any further definitions of what it is to be a point and what it is to be a line. Those are the axioms that give you all of Euclidean geometry. And then you can say that a point is nothing more than the lines that intersect at that point, so the lines that go through that point. So the relationships between points determines the points in that setting too. And then there's an assortment of more arty renderings of the term. So there's this French poet, Paul Valéry, who's, I won't try to pronounce the French, but the English translation of that is it's the execution of the poem that is the poem. So the text of a poem is not the poem. That misses something. There's something lacking in the text that sits there on the page. And the poem is its readings, the collection of all its readings, the way it is performed. So the meaning of the poem is obtained by this interaction between the poet, the reader out of the poem, and the audience who's listening to that, reacting to it, receiving it. And the same idea in music, Theodor Adorno, the idea of interpretation belongs to music itself and is not an accidental thing, not an incidental thing. It's a core part of what music is. So again, the score, the dots and staves, is not a piece of music. that's not Beethoven's Fifth or whatever. Beethoven's Fifth is its renderings, its performances. So again, the relationships between the composer of the piece and the audience, who might be alive at a different time, but that relationship is mediated by the performance. And you see the same in sculpture as well, in physical art. So to understand a piece of sculpture, you have to see it from all angles. And the Yoneda perspective on that tells you all you need to know about the sculpture. It's determined by its views from all perspectives. But returning to Earth, back to more concrete things, if you can read this as concrete things, there's a very direct translation of the category theory statement of the Yoneda lemma and renderings in certain programming languages. So here's a rendering in Haskell, which makes it quite clear. May I ask who can read Haskell to the extent of seeing a data type with a record field like that? About half of you, okay. So this is defining a new data type called Yo for Yoneda, and there's only one variant of this data type, so there's only a single way of constructing this data type. And it's a record with a single field. So that's basically saying that one of these Yo things is just this field. And this field is a function. It's like a method. It's a function that takes an A to X. It's a higher order function. It's a function that takes a function as an argument and gives you something as a result. So you should think of F as being a collection type, like let's say list of things. And f of a is a collection of a's, a list of a's, and f of x is a collection of x's. And this is saying the Yoneda reading of a collection is a mechanism for giving you an f of x if you can turn a's into x's. So this is saying the Yoneda reading of a collection f of a's is a method of yielding an f of x's, provided you can say how to turn a's into x's. And the Yoneda lemma tells you that the Yoneda reading of f is equivalent to f itself. So what does that mean? That means if you have a list of a's and a way of turning a's into x's, then you can make a list of x's. And moreover, the other way around too. If you have a way of taking an a to x mapping and getting back a list of x's, you must secretly have a list of a's. There's nothing else you could do that in. That's the only way you can make a list of x's from an a to x function, is to have in your back pocket a list of x's. And the Yoneda lemma is saying those. So I've explained those two transformations from an f of a and an a to x. You can make an f of x, and conversely, if you have one of these higher order functions, you can get the f of a back again. And the Yoneda lemma says those two transformations are each other's inverses. So this type is isomorphic to that type. Which is to say, if you wanted one of these, you can represent it by one of those. And if you want one of those, you can represent it by one of these. And there's the conversions are quite straightforward. In one direction, if you have an f of a's and a way of turning a's into x's, how do you make an f of x's, so a list of a's and an a to x function? You can make a list of x's by mapping the a to x function over the list of a's. Conversely, if I have a collection of a's in my back pocket, and I say, you give me any a to x function, and I'll give you a collection of x's, and you want to see what I've got in my back pocket, you just give me the identity function, and then you'll get back the collection of a's, and you'll get to see what I have in my back pocket. So in one direction, you use the map, which is it's called a functorial action. It's a way of lifting a data type like lists to an operation, mapping on lists. And in the other direction, you apply to the identity function. And that pattern is characteristic of the Yoneda lemma, and we'll see it coming back again. In one half of an isomorphism, you apply to the identity function, and in the other half, you use the functorial action. There's a very cool dual representation as well. this thing with polymorphic types, and using a little bit of calculation with types, you can turn it into a thing with an existential type. Now, I'm not going to interpret all that for you, but the end result, this thing here, is saying this collection, but so this is a mapping in one direction, but Yoneda again tells you that it's an isomorphism, you can go back and forth. So this is, well, I've changed my A's into X's by doing this, but let me change them back again for comparison with what went before. A collection of A's can be represented by having a collection of X's and an abstraction function from the X's back to the A's again. So you might be thinking of a collection of integers, but representing it by a collection of bit vectors. And you can represent each of the integers by a bit vector. And the Yoneda lemma says those two are equivalent. And that's a useful change of representation technique sometimes. From other bits of mathematics, you see the Yoneda lemma coming up all over the place. So any preordered set can be thought of as a category. So a preordered set is a set of elements A and an ordering, a less than or equal to kind of thing, which is reflexive. Any A is less than or equal to itself, and transitive. If A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. That's the basic ingredients of what it is to be an ordering. And you can read that as a category. I've written it here, the pre-order category based on an ordering. And the categories have objects and arrows. So the objects are the elements of A, and there's an arrow from A to B in the category precisely when A is less than or equal to B in the ordering. So you can take the ordering and read it as a definition of a category. And then what does Yoneda say in that kind of category? The Yoneda lemma collapses exactly into this statement here, that B is less than or equal to A precisely when an arbitrary C is, if A is less than or equal to C, then B is also less than or equal to C. And if you sort of stare at that for a while, you'll see that that means that B must be below A in the ordering. Clearly, if B is less than or equal to A and A is less than or equal to C, then B is less than or equal to C. That's the transitivity bit of the ordering. And conversely, if this works for any C, then you can specialize it to A. A is less than or equal to A, that's true by reflexivity, and that tells you, therefore, that B is less than or equal to A. So you get the other side. So that's the two halves of this equivalence. And this is a very useful rule for proving things about orderings. So proving things about inclusions on sets, proving things about division, proving things about refinements between programs. You can show that one program is less than or equal to another program if they have the same common refinements. So this is a general rule in dealing with ordered sets. There's another one about indirect equality, and I'm not going to explain how this arises, but if you do certain transformations, then the Yoneda lemma collapses again too. Two things are equal in an ordered set when A is less than or equal to C, if and only if B is less than or equal to C. So that's like the previous one, but with both directions, A is less than or equal to B and B is less than or equal to A here, and both directions here. So you can see that they're kind of related. And that's another rule that's used in proving things, this time about equivalences. You have a kind of ping-pong argument. You can show that these two things are equivalent by showing that for any third thing C, either they're both equivalent to it or neither of them is equivalent to C. Here's a third one. Cayley's theorem is this thing from group theory, which is not very familiar to programmers, but there's a simplification of it to monoids, which are much more familiar to programmers. So a monoid is a set of things M, and the binary operator and a constant, such that the binary operator is associative, and the constant is a neutral element for the binary operator. So think addition and 0 on the integers, or multiplication and 1 on the integers, or union and the empty set on sets of things, or sequences of things and concatenation of sequences, that's associative, concatenate y concatenate z is the same as x concatenate y concatenate z, bracketed the other way around. And the empty sequence is the neutral element for concatenation. And the Yoneda lemma tells you that every monoid is isomorphic to a monoid of what's called a monoid of endomorphisms, a monoid of functions here. So this is the function that you get by taking a binary operator and giving it one of its arguments and waiting for the other one. So this is like the function 3 plus, which takes an integer and gives you 3 more than that integer, or the function 4 times, which multiplies an integer by 4, or the function ABC plus plus that takes a string and prefixes ABC onto the front of it. And Yoneda tells you that you can deal with strings, ABC and DEF, or you can deal with their representation as functions, the ABC plus plus function. And Yoneda tells you those two things are equivalent monoids. To go from this one to that one, you just apply the concatenation operator, and to go from that one back to this one, you apply it to the empty list, the neutral element. ABC plus plus the empty list gives you back ABC again. Why would you want to do this? It's useful because depending on how you've represented your strings or your sequences, plus plus takes linear time. So if they're represented as cons lists, as a linked list, it takes linear time to append something to the end of a list, linear time in the left-hand list. But the functions can be composed in constant time. So this is a way of turning inefficient string manipulating functions into efficient function manipulating functions. And this is a standard change of representations that's used it's used, for example, all through the Haskell libraries for the functions, the show functions, the functions that convert things to strings. What you actually define is a show function that works on functions. And these compose very nicely, and then finally you can apply it to the empty string and get back the actual string you want. So much for the Yoneda lemma. Let me now tell you about the other half of the story, these composable references. So these came out of a line of work called bidirectional transformations, and that line of work came itself out of a problem in databases called the view update problem, so from the early 1980s in databases. So here's an example. There's 2 tables at the top of the slide, 2 relational tables. Oops. I was trying to be so slick there. So this is a table of companies, a widget company and a gadget company and a logic company and so on, with locations, a table of parts that these companies make. So the idea is that company ID S1 has offices in London and Boston and makes nuts and bolts, and S2 has offices in San Francisco and Boston and makes rivets and so on. And you can transform that data using selections and projections and joins, so standard bits of gadgets of relational database queries, to say, so what are we doing here? What can I buy in Boston? So I can get nuts and bolts from company S1 and I can get rivets from company S2 in Boston. So this is joining these 2 tables on their common identifier column. That's the relational join here. Selecting the ones that have location Boston, and then projecting away some of the columns because you don't want all of that data. So this is a standard kind of query. And a view in relational databases is a query like this whose result is stored, if you like, made available, manifested. So you can now think of this as being another table in your database. And maybe this is useful because there's stuff in here that's private and you shouldn't see it, or maybe this is useful because this is big and you only want a small part of it. You want to be thinking about this as being the data and hiding that. And the view update problem is, now suppose I think of this as the data and I see something's wrong and I want to change it. So maybe the gadgets company changes its name and I get to change it. so I try and change it. The view update problem is to work out what should happen to the original tables to make that change actually happen, because what you're working on here is only a virtual table rather than an actual table. And it's quite a difficult problem, and it's kept the database community busy for 30, nearly 40 years. And there are lots of papers about it and books about it, and the main database manufacturers do or do not support this variously. It's still quite a thorny problem. But it has many other manifestations as well. So you can see the same thing in user interface design. This is your business logic, and from it you compute some view of the system, and then users interact with the view, and you have to work out what the corresponding changes to the business logic should be to support that change. And there are lots of other applications too that I won't go into. This found its way into programming languages through some early work in the 1990s by Koji Kagawa and Frank Oles on what was called compositional references at the time. So here I have some complicated data, and so this consists of a 4-tuple and a 3-tuple and a 2x2 thingy, and there's a projection that extracts this 3-tuple from the main part of the data. But then this itself is composite, and I'd like to be able to project the E part out of that triple. So a compositional reference is a way of saying that this triple is part of this egg-shaped thing, and the square is part of the triple in such a way that you can say the square is part of the egg-shaped thing. So obviously you can extract, you can get the triple out of the egg-shaped thing. That's just a projection. And if you update this with a new one, you will hopefully be able to put it back in again. So that's kind of like a getter and a setter for some field in a composite object. And here I have a getter, and I'd like to have a setter for that as well, and I'd like to be able to compose these things. Came through into more modern functional programming, more modern programming language parlance in the work of Nate Foster and Benjamin Pierce about 10 years ago, and they call these things lenses. So a lens is a pair of functions. So there's a type there, a source type S, and a view type V. So there's one function, which is the projection, that given the source will give you the view. So that's just a straightforward function from S to V. And then you'd like to be able to update the view. So you now have a new view, V prime, and you want to put that back to update the source to get S prime. There isn't enough information in the view just to go from V prime back to S prime. You need V prime and the old S together to make the S prime. So a lens consists of a get function from S to V, and a put function from V prime cross S to S prime. So it takes a pair, the updated view and the old source, and merges them together to make an updated source. So in Haskell, they're represented as follows. I've changed my variable names now, but the getter function I've called view here goes from the source to the view, and the setter function, which I've called update, takes an updated view B and the original source S and produces a new view T. And I can represent that as, this is Haskell syntax for a record with a pair of functions, a pair of fields which are both functions. So a lens is a pair of functions, the getter function called view and the setter function called update. So for example, an A cross C pair consisting of an A and C, has an A in it. So there's a getter function that will give you the A, that's just to project the first component of the pair. And then there's a setter function that, given a new value A prime, will overwrite the old value A and give you a new pair, A prime comma C. So that's a lens. This is a piece of data, it's a record with two fields that is of this type. So that's lenses, and they're very useful. They're used all over the Haskell ecosystem in complicated systems. For example, in the GHC, the main Haskell compiler, uses lenses for accessing fields of records, and it works quite nicely. They have a nice dual, which has been called prism, so continuing this kind of optical metaphor. And the picture is very similar. So what's changed is just the little curly arrow moves from one place to another. Think of a sum type, like think of an abstract superclass and two concrete subclasses. You have shapes, and you have circles, and you have rectangles. So a shape is either a circle or a rectangle. And if you want to do circly things to something that is given to you as a shape, you have to downcast it from a shape to a circle, then it's a circle and you can do circly things to it, and then you can upcast it back again to being a shape. So the upcast is straightforward. Upcasts always work. Every circle is a shape. That's fine. It's the downcast that is the tricky thing, because downcasting a shape to a circle might succeed and give you a circle, or it might fail. So what's going on here is my shape matches the downcast thing, and it either gives me a circle or does something else. Why does it go around there? Well, let me come back to that. But then you do circly things, and you get an updated circle, and you can easily upcast it. That's called build. And the types, trust me, work out as follows. So, for example, here's a simpler example, an optional value, which in Haskell is written with the maybe type operator. So maybe int is the type that has integers in it, optional integers in it. So they're either just an integer, just 3, just 5, just 7, and so on, or nothing, to say it's an optional 1 and it's not there in this case. So if I want to do integer things to an optional integer, I can downcast my optional integer to an integer, double it, and upcast it back again. The upcasting just puts the just around the outside, that's easy. The downcasting says, well, sometimes it works and sometimes it doesn't. And so you get a sum type here, and if it was an optional thing that is not an integer, is an absent integer, then straight away it's an absent updated integer as well. You don't need to do anything different to make it an absent updated integer. Similarly with shapes and circles and rectangles, if you want to turn your circle into an oval, so a shape is a circle, and an old shape is a circle or a rectangle, and a new shape is an oval or a rectangle. You can downcast your shape, and if it's a circle, you turn the circle into an oval, and then you upcast it, and then you've got a new shape, which is an oval or a rectangle. And if your original shape was a rectangle, and you downcast it, well, it's already an oval or a rectangle, so you don't need to do anything to make it into the new kind of shape. So that's kind of a hand-wavy explanation of why this downcast either gives you the view or straight away gives you the updated source. So again, trust me, this is how it works out. In the interest of speed, I'll move on. I'll point you to a paper at the end if you want to read more about this. They have a common generalization, sorry, a common specialization, which has been called adapters. So these are shims that you can plug around components if they ought to fit together morally, but they just don't because things are in slightly the wrong format. So suppose I have a choice of A values, an A value represented this way or an A value represented that way. Another representation is just as the A value with a Boolean flag to tell you whether it's the left kind or the right kind. And suppose I have one of these and I want to use it in an environment that expects one of those, well then I have an adapter that turns all cross A's into A plus A's and then back again A primes plus A primes into all cross A primes. And you can think of a lens as being an adapter, a degenerate. No, you can think of an adapter as being a degenerate lens where the view is the whole thing. So think of a record with just a single field. You can get that field, fine. When you update the field, you actually didn't need the old source, the old record, because you're going to replace the whole of it with this single field. So if the update can do without, sorry, doing that again, if the update can do without this curly arrow here, then you have a straight through arrow from S to A and a straight through arrow from B back to T, which is one of these adapters. Similarly, if you have a superclass with just one subclass, you downcast, and the downcast always works, so you don't need the curly escape route, so in case it doesn't work, because it's never not going to work. So an adapter is also a degenerate prism, so that's why it's a common specialization. Now, the thing about these optics is they compose mostly. So two lenses make a lens. If you have a record with a field, and that field is itself a record, then you can get one of those inner fields out. And how do you do that? Well, the getter for the outer thing gives you the inner record, and then the getter for the inner record gives you the field. So you just compose those two getters, and you'll get the original field. You get the inner field. And how do you update? Well, it's a bit more involved, but given a composite record and a new value for one of the inner fields, you want to extract the inner record and then overwrite the field and then overwrite in the outer record. So two lenses can be put together in a certain way with a bit of plumbing to make one lens that gives you access to the composite thing. And that's this compositional reference that's going on here. If you can get the EFG out of the egg and you get the E out of the EFG, then you can get the E out of the egg. Conversely, if you can update the EFG in the egg, then you can update the E in the EFG, then you can update the E in the egg. They compose. And the other things do too as well. Two prisms compose to make a prism, two adapters compose to make an adapter. Because adapters are special cases of lenses, an adapter is a lens, a degenerate one. So an adapter and a lens is really just a lens and a lens, so that composes to make a lens. And an adapter and a prism is really a prism and a prism, and that composes to make a prism. So adapters compose nicely with other things. But lenses and prisms don't compose. So, for example, shapes, circles, and rectangles again. Suppose I wanted to do widthy things to my shape. In order to do that, I'd have to downcast it to a rectangle, that's a prism, and then get the width field, that's a lens. But the pair of those two functions, the downcasting and the projection, it's not a lens because it won't always give you a width. To be a lens, it would have to always give you a width, and it doesn't always give you a width. And it's not a prism because, given an updated width, you can't freely upcast it to make a shape again. You don't have enough information. So it's neither a lens nor a prism. It's a different kind of animal. So that's the sense in which these nice optics, lenses and prisms, are not compositional references. They're mostly compositional, but not quite fully compositional. And here's the clever bit. There's this alternative representation of optics, so things like lenses and prisms and adapters, as what's called profunctor optics. So a profunctor optic is just a change of representation. It's a different way of presenting that record with a pair of functions as a higher order function. So let me give you the idea. What's the profunctor bit in there? Profunctors are, you can think of them as being transformers. So they're things that consume and produce stuff. So this picture on the right-hand side is a transformer. It's intended to show that it takes A's in and produces B's out. So it's a bit like a functor, a collection. It can give you B's. There are B's in there, and you can get B's out of it. But it's a collection that produces B's, but consumes A's as well. So it's a box that will deliver B's to you, like a list can, but it's one that will take A's in as well. So these are ways of transforming some number of A's into some number of B's, is the idea. And they have a functorial action. They have a mapping thing that's like the map for lenses, except because these are not just producers of stuff, but consumers and producers of stuff. The mapping thing takes two arguments. One to modify the products, the things that get produced, and another one to modify the things it consumes. the consumpts, if that's a word. So if you have something that produces B's and a way of turning B's into D's, you can have something that produces D's. You just plug this modifier on afterwards. If you have something that consumes A's and you want to turn it into something that consumes C's, you have to plug an adapter on the front, a modifier on the front. And if you think about it, that's not an A to C function, that has to be a C to A function because it has to go on the front. This is called contravariance. So you need a C to A modifier, which you can stick at the top, and then a B to D modifier, which you can stick at the bottom, and that will turn this A to B transformer into a C to D transformer. So that's why this opposite thing is going on here. It's contravariant in one of its parameters. And there's some classes of that for dealing with product types and dealing with sum types. And I'm not going to say anything, any more detail about that, but just a refinement of the idea. So the canonical transformers are functions themselves. So the arrow type, arrow AB, is things that consume 1A, precisely 1A, and gives you precisely 1B. But there are many other things that are profunctors too. And then a profunctor optic is same kind of box, but now a different implementation. So I'm hiding the implementation. But the implementation is as follows. So this is the profunctor way of doing adapters. It's not going to be a function from S to A and another one back from B to T. Instead, it's going to be, if you tell me how to turn the A's into B's, I'll turn the S's into T's. So I don't trust you enough to give you actual A's to deal with. So there's not going to be a getter that will yield an A to you and then go and run away with. I'm going to hang on to the A's. But if you want to modify them, if you want to update them, if you want to double them or rotate them or whatever it is you want to do to those A's, just tell me, give me the function, the profunctor, the transformer, tell me what you want to do to those things, and then I will go ahead and do it. So I will act on the A in context and give you an updated thing, a T. So that's what this type here is saying. An adapter in this profunctor representation with these 4 type parameters is something that if you can turn A's into B's with some transformer type, then I'll lift that to being a way of turning S's into T's. So that seems obscure, perhaps. But the first thing to note is that this box is just represented as a function with some complicated thing on the left and some complicated thing on the right, but it's just a function. And that means, provided the types match up, you can compose 2 of these boxes just by composing functions. They are just functions. So whereas before we had a record with 2 fields and you had to do something clever to figure out how to compose 2 of those records to make another record, now they're just functions, so you can just use function composition. As long as the types work out, and they will. So that's for adapters. Lensers are precisely the same kind of thing, but they're allowed to assume something more about the profunctor. It's not just an arbitrary profunctor, it's one of this subclass of profunctors that knows how to deal sensibly with products, because lenses are something to do with products. Why is this the right definition? Well, you'll have to go and read the paper for that, but trust me, it is. And so that's lenses. They're just the same kind of thing, but they're allowed to make another assumption about the class of transformer that's being used. And prisms, well, again, they're just the same kind of thing, and they're allowed to make a different assumption about the class of transformers that are being used. But then the sweet thing is that now a lens in this presentation and a prism in this presentation can compose, so we can do our witty things on shapes, just by composing the functions, as long as you make both assumptions. So you're allowed to assume that the transformer you're doing behaves nicely with respect to products and behaves nicely with respect to sums. So it's it's like a multiple inheritance. It's assuming both of these subclasses of profunctor. And there are plenty of profunctors that are members of both these subclasses. That means you can compose your lenses and prisms and do plenty of things to them. So in particular, if you want to operate on the width and turn it into something else, you can lift that to operating on the width field of a record that is not cast to a shape. A width field of a rectangle that's not cast to a shape. What have these two parts of the talk got to do with each other? Well, they're to do with the question, what have these two representations of optics got to do with each other? So we had the concrete representation. A lens is a record with a pair of functions, a prism is a record with a pair of functions, an adapter is a record with a pair of functions. And I showed you a different one. A lens, a prism, and an adapter are just certain higher order functions. And I gave you kind of hand-wavy arguments as to why they're related to each other. But we might want a more robust argument as to why they're related to each other. And it all boils down to Yoneda, of course, which is why the talk has those two halves of it. So the key insight is this result using the Yoneda lemma twice and this variant of the Yoneda lemma. So there's three applications of Yoneda, but it's really the Yoneda lemma used twice. And it's a result by a clever guy called Bartosz Milewski, who, well, in a sense it's obvious because Yoneda is so well known and is just putting it together twice. In a sense it's beautiful because I mean, the whole proof of that result is on the slide together with the statement. It's just three little steps. Whether you make sense of the steps depends on whether you make sense of the Yoneda lemma and the category theory, and it's all there. I'm not hiding anything, but you do need to stare at it for a while in order for it to become natural language. But this is the key result. And what it boils down to is the following equivalence. A way of turning a collection of A's into a collection of B's that works for any collection F, any collection F, so lists or trees or matrices or arrays or pairs of things or whatever, can only be an A to B function. If you have an A to B function, you can turn a collection of A's into a collection of B's for any collection because you can just use the functorial action as the collection type. So if it's list, you use map for lists, and if it's pair, you use map for pairs, and so on. Conversely, if you have one of these gadgets that works for any collection type, you can apply it to the singleton collection type, the identity functor. The identity functor is just an A. So this works to turn a collection of A's into a collection of B's, so let's make it turn a singleton collection of A's into a singleton collection of B's. So that's essentially an A to B function. So that's the two halves of the transformation. You have to check that they're each other's inverses, but trust me, they are. And again, you see, in one direction it's the functorial action, in the other direction you apply to the identity functor, as it happens. So it's two halves of Yoneda. So this is the equivalence in just as Haskell functions, but it works in any category. And in particular, it's going to work for our optics. How does this pan out? So remember, a concrete adapter, the record with a pair of functions, is a function from S to A and a function from B to T. Now, I can read that as a function from AB thingies to ST thingies, which operates backwards on the first components of those, on the A and the S thingies. And that happens to be just what the profunctor representation of adapters was. If you can turn AB transformers, there's a way of lifting an AB transformer into an ST transformer. It's a mapping from left to right. So this pair of arrows, S to A and B to T, is just the profunctor adapter that turns an arbitrary transformer of A's into B's into the transformer of S's into T's. And you can render all that in category theory by defining a new category and looking at the arrows in that category. But then if you just apply Bartos's clever lemma, in that category theory, what you get is precisely the statement that the profunctor representation of adapters amounts to these pairs of arrows, is equivalent to these pairs of arrows. So, again, if you haven't assimilated, if Yoneda is not your friend yet, if you haven't completely assimilated the Yoneda lemma and got it in your bones, then it'll take you a while staring at that to see that. It certainly took me a while staring at it to see it. But it's there, and it's all there on the slide. There's nothing more, well, there's proofs. Again, they're short things. So that's the story for adapters. What about lenses and prisms? Well, it's similar, except you just have to think about, you can't just think about them as individual unconnected pairs of arrows, because lenses are a bit more complicated than that. But it turns out that another way of thinking about a lens is take your source and factorize it into the view and everything else, sometimes called a complement. And then that's the getter, and then the setter takes the updated view B and the same complement and packs them back together again. So this is an arrow from S to the factorized representation of the view and the complement, and then this is the setter that puts them all back together again. So these are equivalent to concrete lenses, the view and update function, and Bartos's clever lemma shows that these things are equivalent to the profunctor representation. So it's again, it's a two-step equivalence. And the same thing works for prisms, and it works for a whole bunch of other kinds of optics. They're called access mechanisms. So it works for things where you have several elements and you want to access each of them, a traversal over the elements of a container. So there are proofs, but I'm not going to talk through those, and I'm going to end there. So just to summarize, these profunctor optics are very practical. They're very simple, and they compose very sweetly just as functions. So they are now the favourite representation of these getters and setters kind of things in the Haskell libraries. They're mysterious on the face of it. What's the connection between these things? How would you come up with these things? But there's a very simple proof that the fancy higher order representation is the same as the concrete representation, and it just boils down to little uses of the most important result in category theory, the Yoneda lemma. So there are lots of people who've worked on this before me, and I'm basically collecting and presenting their ideas. And the content of this paper is, as I say, the work of my student Guillaume Boisseau, my PhD student, who's funded by the UK EPSRC. If you want to read more about it, it was a paper at ICFP this year by Guillaume and myself. It's on my webpage. It's called Profunctor Optics and the Yoneda lemma. That's the subtitle. The title is What You Need to Know About Yoneda. And I encourage you to read it. And I'll stop there.
So, any questions? Right, hang on then. Here you go.
Thanks for the great talk. Sort of abstracting. We have these classic lenses, we have profunctor lenses.
Yes.
Profunctor lenses are composable, and they're equivalent to the classic ones, which means that classic ones are also composable.
Well, except that, no. So the profunctor ones include all the classic ones. So there's a profunctor representation of lenses that is equivalent to the classic representation of lenses. There's a profunctor representation of prisms that's equivalent to the classic representation of prisms. But there are things in profunctor world that aren't equivalent to anything in the classic world. And if you compose stuff in the profunctor world, you might end up outside things that correspond to the classical world. So it's a bit like taking the problem on real numbers and reading it as in complex space, in the complex numbers. The real numbers can be seen as complex numbers, and there are complex numbers that correspond to every real number. But you might do all your problem solving and end up with an imaginary result, which is kind of what the profunctor things are. And then there's no way of just saying, I could have done it in real numbers in the first place. I've ended up with an imaginary root in my quadratic equation, or something like that.
Okay.
Right. Anyone else?
Good question.
Right then. So, thank you very much.
Okay, thank you.